All right, let's just dive right into this. Think about every single image you've ever seen a neural network analyze, or every sentence ChatGPT has ever generated for you, every sound wave, every video frame, and honestly, every single one of the billions of learn parameters sitting inside an AI. Believe it or not, all of that, literally all of it, eventually collapses into exactly one mathematical object. Today, in this explainer, we're going to look really closely at what that object is, how it's structured, and why it is the absolute foundation of modern artificial intelligence.
And that object is the tensor. Now, I want to clear something up right away. A tensor isn't magic, and it's definitely not some brand new sci-fi invention created specifically for AI. It's actually just a beautifully logical container for numbers that's existed in math and physics for a very long time. Deep learning frameworks like PyTorch and TensorFlow adopted it simply because, well, it's the perfect structure to hold absolutely vast amounts of data.
So here is our roadmap for this explainer. We're going to cover 1. From scalars to tensors. 2. Anatomy of a tensor. 3. Core tensor operations. 4. Batching and hardware power. 5. A tensor's GPT journey. And finally, 6. Advanced tensor insights. Let's get to it.
Kicking things off with Section 1, From Scalars to Tensors, where we build up the dimensions.
Okay, let's build this up conceptually. We start with a scalar. A scalar is literally just a single number, like the number 7. It has 0 dimensions, so you can think of it as just a single dot. Mathematicians call this a rank 0 tensor. Step 2 is a vector, which is an ordered list of numbers. That adds 1 dimension, kind of like a line of dots, making it a rank 1 tensor. Step 3 is a matrix, a 2D grid of numbers with your standard rows and columns. That's a rank 2 tensor. Notice this beautiful progression here, right? Every step adds exactly 1 dimension. So what happens when we step beyond a 2D grid? Well, that is your tensor in the traditional deep learning sense, a 3D, 4D, or even higher dimensional container.
Now, you might be sitting there wondering, why do we even need anything beyond a 2D matrix in the first place? Well, think about how you'd represent a color image. A matrix is great for a grayscale picture, but a color image, that needs 3 grids stacked together. One for red, one for green, and one for blue. And what about a video? A video is just a stack of those color images changing over time, so boom, we need another dimension. What about complex audio waves, or processing a massive batch of multiple videos all at once? We need yet another dimension. A single 2D matrix literally just runs out of room. We absolutely have to have a mathematical object that can hold data across 3, 4, or way more dimensions all at the exact same time.
Moving right along to Section 2, Anatomy of a tensor. It's time to learn the vocabulary.
So, formally speaking, a tensor is just a container for numbers organized across any number of dimensions, which we call axes. As we just saw, scalars, vectors, and matrices are technically just special low-rank tensors. But when deep learning engineers say the word tensor, they are usually talking about these massive, glowing mathematical grids with 3, 4, or more axes.
Okay, we need to clear up a massive beginner confusion right now, because people mix these 4 terms up all the time. Look closely at the distinctions here. Rank is strictly the number of axes a tensor has. Dimension is kind of tricky. Sometimes people use it to mean rank, but sometimes they use it to mean the actual size of one specific axis. Shape is a tuple. It tells you exactly how big the tensor is along every single axis. And size is simply the total number of individual data elements inside the whole tensor, which you get by just multiplying all the shape values together.
Let's actually practice reading some of these tensor shapes out loud, because this is a super practical skill to have. A shape of 28 by 28, that represents a standard 2D grayscale image. 224 by 224 by 3, that's a 3-axis tensor representing a color image with those red, green, and blue channels we talked about. Now look at 32 by 224 by 224 by 3. The absolutely crucial point here is that the leftmost dimension typically represents the batch slice. So that right there is a batch of 32 separate color images. And finally, 512 by 768 represents a batch of 512 language tokens, where each token is represented by a 768 number vector. This is exactly what data looks like under the hood inside an AI.
All right, Section 3. Core tensor operations, or how we bend the grid.
You are going to see these operations constantly in AI code. Reshape just rearranges the numbers into a different shape, kind of like pouring water from a wide bowl into a tall glass. Squeeze removes an axis that only has a size of 1, while unsqueeze does the exact opposite, adding a brand new axis of size 1. Permute and transpose completely swap the order of the axes around. When you need to combine data, concatenate glues tensors together along an existing axis, whereas stack creates a brand new axis to stack them on.
And finally, broadcasting is this brilliant underlying rule that automatically stretches smaller tensors out to match larger ones during math. The big takeaway here? All these operations reorganize the data, but they never ever change the underlying meaning of those numbers.
Next up, Section 4, Batching and Hardware Power. Let's talk about why GPUs absolutely love tensors.
So why don't we just feed neural networks one image at a time? Well, this brilliantly illustrates why. If you process a single color image, it's like moving at a snail's pace. Your graphics card, or GPU, basically just sits there mostly idle. See, GPUs have thousands of cores designed for massive parallel computation, but by bundling 32 images into a single batch tensor, boom, we get rocket ship speeds. The GPU can perform the exact same math on all 32 images simultaneously. Batching is for sure the absolute key to fast AI, and tensors are the exact container that makes that batching possible.
If you ever write AI code in something like PyTorch, there are 3 crucial properties of every tensor that you'll be tracking constantly. First, you always check its shape so you understand its dimensions. Second, you check its D-type, which is the numeric format, like float32 for standard decimal numbers. And third, you check its device to see if the tensor physically lives on your computer's slower CPU or if it has successfully been moved over to the ultra-fast parallel GPU. Honestly, getting all 3 of those right is pretty much the daily life of an AI developer.
Which brings us to Section 5, a tensor's GPT journey. Let's trace the computation graph.
This is the epic life cycle of data as it flows through a large language model. First, your raw text tokens become an embedding tensor. When multiple sentences are bundled up, they become a batch tensor. As the data flows deeper into the model's logic, it forms an attention tensor, which captures exactly how words relate to each other. Between the layers, it's called an activation tensor. The AI's actual learned knowledge is stored in weight tensors, and the signals used to train those weights are gradient tensors. Finally, after all that incredibly complex math, the whole thing condenses down to a single rank 0 scalar value, the loss tensor. When you zoom out, GPT is fundamentally just one giant tensor computation graph.
Finally, Section 6, Advanced Tensor Insights, where we push the limits.
When you start looking at massive LLM training code bases, you'll see things like einsum notation, which is a highly compact way to combine tensors using tensor contraction. You'll see named tensors that actually attach text labels to axes to prevent nasty bugs, and sparse tensors that save tons of memory by only storing non-zero values. But the absolute crucial point here is mixed precision. Standard data is 32-bit floating point, or FP32, but AI engineers actively shrink their tensors down to 16-bit formats like FP16 or BF16. It's slightly less mathematically precise, sure, but it uses half the memory. And that is absolutely essential if you want to fit these gigantic models onto your GPUs without running out of space.
So, we've covered the complete anatomy of a tensor today, from a simple little dot all the way up to massive data batches, and we've seen how they flow through an AI. But this leaves us with a pretty massive question. We know exactly how to organize the data now, but how does the neural network actually compute with it? Like, how do we calculate meaning and generate actual words? Well, that requires vector operations, like the dot product. And that is exactly what we are going to unpack in our next explainer. Thanks so much for joining me on this deep dive into tensors.